Welcome back to this series on the stiffness method. Until now, we've seen how to assemble stiffness matrices into a global stiffness matrix when the local matrix axes were aligned with the global matrix axes. In reality, however, structures are not that neat, and usually we will find inclined members. So today we'll be looking at how to rotate each element from its local stiffness matrix to the global stiffness matrix and assemble them together. So far, we've derived local stiffness matrices for different element types, and we've assembled them into a global matrix in the simple case of straight members aligned with a global axis. But real structures are rarely this neat. Members are usually inclined, and their stiffness matrices must be transformed to fit into the common global coordinate system. Once we master this step, we'll be ready to tackle the transformation of load vectors and then solve the matrix for displacements, reactions, and internal forces. Each element's stiffness matrix is first written in its own local coordinate system, which is aligned with the axis of the element. That makes the mathematics much simpler, because the behavior of the member is expressed directly along its own length. But because every element may be oriented differently, we need to convert these local stiffness matrices into a global coordinate system. The global system is shared by the entire structure, and it is in this system that the full set of equations must be assembled. If we look at the truss from before, the global coordinate system is the XY system shown here. However, if we look closely at the diagonal members, its local coordinates are aligned along the axis of that member, not along the global axes. This transformation step ensures that all elements, whether horizontal, vertical, or diagonal, are described consistently. Only when they are expressed in the same global system can they be assembled together into one global stiffness matrix for the whole structure. Let's look more closely at a single element in the truss. Every element is easiest to describe in its own local coordinate system, where the local x-tag axis runs along the member. For this bar, the local x-tag axis does not line up with the global x-axis. Instead, it's rotated at an angle theta. The angle theta is the key link between the local axis of the element and the global coordinate system. In the local system, displacements and forces are measured along the axis of the member. But to assemble the whole structure, we need to describe the same quantities in the global XY system. And that is why angle theta is so important. It allows us to transform between the two systems. To transform the element into the global coordinate system, we project its local axes onto the global axes. The local x-tag axis is rotated at an angle theta to the global x-axis. If we drop a perpendicular line from the tip of the local axis to the global x-axis, we obtain its horizontal projection, which is cos theta. We can also project onto the y-axis and obtain the vertical component, which is sin theta. These projections define how the local coordinate system relates to the global system, and they form the foundation of the transformation matrix that we will use to rotate displacements, forces, and ultimately the stiffness matrix into global coordinates. We can also express these projections algebraically. The local x-tag axis is made up of a horizontal component, cos theta in the x direction, and a vertical component, sin theta in the y direction. In vector form, we can write this as x-tag equals x cos theta plus y sin theta. Similarly, the local y-tag axis is minus sin theta in the x direction and cos theta in the y direction. Together, these equations capture exactly how the local coordinate system relates to the global system, and they lead directly into the construction of the transformation matrix. From the previous slide, we saw that the local x-tag axis can be written as cos theta in the global x direction and sin theta in the global y direction. In the same way, the local y-tag axis can be written as minus sin theta in the global x and cos theta in the global y. If we put these two equations together, we can express them in matrix form. The local axes, x-tag and y-tag, are equal to a 2 by 2 matrix multiplied by the global axes x and y. The entries of this matrix are simply the projection factors cos theta, sin theta, minus sin theta, and cos theta. This 2 by 2 matrix is called the rotation matrix R. It provides a compact way of expressing how the local coordinate system is related to the global system. And this matrix is the fundamental building block for the full transformation matrix that we will use in structural analysis. In the local system, each node of a truss element has only one degree of freedom, displacement along the axis of the element. In the global system, however, each node can move in two directions, horizontal and vertical, and that means that each node has 2 degrees of freedom in the global system, u and v. At node 1, the local displacement, u tag 1, is related to the global displacement by the geometry of the elements. So u tag 1 equals u1 cos theta and v1 sin theta. The same relationship holds for node 2. u2 tag equals u2 cos theta and v2 sin theta. If we collect these equations together, we can write them in matrix form. The two local displacements, u1 tag and u2 tag, are equal to a matrix multiplied by the 4 global displacements, u1, v1, u2, v2. This matrix is the transformation matrix T for a truss element, and this is what allows us to connect the 2 degrees of freedom in the local coordinates to the 4 degrees of freedom in the global coordinates. With the transformation matrix defined, we can now describe how displacements in the two systems are related. Local displacements are obtained from the global ones using u tag equals the matrix T, the transformation matrix, times u. Equally, we can invert the relation to express global displacements in terms of local ones. So u equals T transpose times u tag. This shows that the transformation matrix and its transpose gives us a two-way link between the local and global displacement vectors. This result sets the stage for transforming the stiffness matrix itself. We start off in the local coordinate system, where everything is defined along the axis of the element. In this system, the equilibrium relationship is written as F tag equals the local K matrix times the local displacements U tag. Remember that for a truss element, this is a 2 by 2 matrix because each node only has one displacement degree of freedom in the local axis, the axial displacement along the member. Now we know that the local displacements are related to the global displacements through the transformation matrix. It means that if we know how the nodes move in the global x and y directions, we can then resolve those motions into displacements along the local axis of the member. If we substitute this displacement relationship into the local stiffness equation, we obtain that F tag equals K, the local stiffness matrix, times T, the transformation matrix, times U, the global displacements. At this point, notice what has happened. The displacements are now expressed in the global system, but the forces are still in the local system. So we're halfway there. The next step is to bring the forces into the global system as well. In the global system, we want the equilibrium relationship to be written as the forces equal the global stiffness matrix times the global displacements, where both the force vector and the displacement vector are expressed in global coordinates. To make this transition, we use the relationship that the forces F equal the transpose of the transformation matrix times the local forces. This step ensures that the forces are rotated from the local system into the global system, just as we rotated the displacements before. And now we can substitute again. So if F tag equals the local K times the transformation matrix times the global U, then the global F equals T transpose times the local stiffness times T, the transformation vector, times U, the global displacements. Here, everything is expressed in the global coordinate system. The product, T transpose KT, plays the role of the global stiffness matrix. And the final step is identifying the global stiffness. By comparing the expression with the general equilibrium form, F equals KU, we can identify that the global stiffness matrix is T transpose times the local matrix K times T, the transformation vector. Now that we have the expression for the global stiffness matrix, let's look at the sizes for each term. The transformation matrix T has a size of 2 by 4 because it maps 4 global displacements into 2 local displacements. Its transpose, therefore, has a size of 4 by 2. The local stiffness matrix is 2 by 2, and so the product is a 4 by 2 matrix times a 2 by 2 matrix times a 2 by 4 matrix. Matrix multiplication is associative, meaning that we can group it either as T transpose times K times T, or as T transpose times K times T. But it is not commutative, so we cannot change the order. Either way, the end result is a 4x4 global stiffness matrix. And this makes sense because each truss element has two nodes and each node has two global degrees of freedom. Now we can see what the global stiffness matrix actually looks like when it's expanded. We start with a local stiffness matrix for a truss element, which is a 2x2 matrix scaled by EA over L. Applying the transformation K equals T transpose times K times T, the global stiffness matrix becomes a 4x4 matrix. Notice how the terms are built from combinations of cos theta and sine theta. The diagonal entries involve the cos squared or the sine squared, and the off-diagonal entries involve cos and sine. The symmetry of the matrix is preserved. And this expanded form clearly shows how the orientation of the element through theta directly influences the stiffness contributions in the global system. Let's do one full numerical pass to make the symbols make sense. So if you have a bar at a 45-degree angle, cos theta equals sine theta equals a square root of 2 over 2, which is roughly 0.7071. We start off with a local 2x2 stiffness matrix. K equals EA over L, and in the matrix we have 1s and minus 1s. We use K equals T transpose times K times T, and substituting C and S, or cos and sine, gives us the 4x4 matrix shown. Note the structure. Diagonals are 0.5 EA over L. Off diagonals are plus or minus 0.5 EA over L. And the matrix is symmetric. And this matches our intuition. A 45-degree bar shares stiffness equally between the global X and global Y directions. Having seen how we handle a truss element with only axial behavior, the next step is the beam or frame element. This element has two nodes, but each node carries 3 degrees of freedom. A translation in X, a translation in Y, and a rotation around the Z-axis. That makes 6 degrees of freedom in total. The local axes are aligned with the member, just like in the truss. The local stiffness matrix is therefore, as we've previously discussed, a 6x6, and it combines both the axial stiffness terms, EA over L, and the flexural stiffness terms involving EI. This matrix is the starting point for transforming beams and frames into the global coordinate system. To transform a beam or frame element from local to global coordinates, we need a 6x6 transformation matrix. The matrix uses cosines and sines of the element's angle theta relative to the global x-axis. The translational degrees of freedom are rotated using the trig terms, while the rotational ones remain unchanged. This transformation ensures that all displacements and forces can be consistently compared in the global system. The global stiffness matrix for a beam or frame is obtained in the same way as for a truss. We take the local stiffness matrix and apply the transformation T transpose K T. This operation expresses the element stiffness in global coordinates, which allows us to assemble it directly into the overall global stiffness matrix of the full structure. By working in global coordinates, we ensure that each element is fully compatible with the rest of the system. The procedure for a beam or frame element follows 4 clear steps. First, compute the trig values of cos theta and sine theta for the element orientation. Second, write down the 6x6 local stiffness matrix, which combines axial shear and bending stiffness. Third, apply the transformation K equals T transpose KT using the 6x6 transformation matrix. And finally, this gives us the global stiffness matrix, where the axial and bending effects are now coupled. At this stage, you can see that the manual calculation becomes much heavier than we did for the bar element. 6 equations instead of 4 and more complex terms. This is exactly the point where programming the stiffness matrix really helps. In the next step, we'll use a truss example and compute a global system in full and see how the process is implemented in practice. We're now ready to work through a complete example with a simple 3-member truss, which we will then code. Don't worry, we'll also code the transformation for a beam frame element, but we'll leave that till next time where we have more things to add. This is a 3, 4, 5 right-angled triangle. Node 1 is at 0, 0 coordinates, node 2 is at 3, 0, and node 3 is at 3, 4. The three bars are between nodes 1, 2, 2, 3, and 1, 3. From the node coordinates, we can determine the geometry of each element. Member 1, 2 is horizontal with a length of 3, so the cosine is 1 and the sine is 0. Member 2, 3 is vertical with a length of 4, so the cosine is 0 and the sine is 1. And member 1, 3 is diagonal with a length of 5 and a cosine of 3/5 and a sine of 4/5. Each node in the truss has two possible displacement degrees of freedom in the global coordinate system: a horizontal displacement, which we label capital U, and a vertical displacement, which we label with a capital V. On these diagrams, we can see these drawn as arrows at each node. Node 1 has degrees of freedom U1, V1, node 2, U2, V2, node 3, U3 and V3, and altogether this gives us 6 global degrees of freedom. These are the reference points for assembling the stiffness matrices. Each element's stiffness will connect the degrees of freedom at its two end nodes, and we'll use this structure to build the full global stiffness matrix. We now substitute the geometry of each member into the general stiffness formula. For member 1, 2, the bar is horizontal, so the cosine is 1 and the sine is 0, and the length is 3. The resulting stiffness matrix couples only the horizontal displacements of node 1 and 2. Notice here that the bar lies along the global x-axis, so the local and global axes coincide, and this means that the transformation has no effect. The local and global stiffness matrices are essentially the same. For member 2, 3, the bar is vertical, so C, the cos equals 0, and the sine S equals 1. The length is 4. This stiffness matrix couples only the vertical displacements of node 2 and 3 with all the terms involving horizontal displacements equal to 0. For member 1, 3, the bar is diagonal and the cos C equals 3/5 and the sine 4/5. Substituting these values produces a full 4x4 matrix containing a combination of cosine square, sine square, and cosine times sine. This is the only member that introduces coupling between horizontal and vertical displacements. These three matrices are the element contributions. On the next slide, we'll assemble them into the global stiffness matrix of the whole truss, placing each submatrix into the rows and columns corresponding to its node's degree of freedom. Now we assemble the global stiffness matrix by placing each element's contribution into the rows and columns corresponding to the nodal degrees of freedom. The global displacement vector is ordered as capitals U1, V1, U2, V2, U3, V3. So our global stiffness matrix is a 6x6. For member 1 to 2, its 4x4 stiffness matrix connects nodes 1 and 2. So we place it in the rows and columns corresponding to degrees of freedom U1, V1, U2, V2. For member 2 to 3, we place its 4x4 contribution into the positions for degrees of freedom U2, V2, U3 and V3. For member 1 to 3, we place its matrix into the rows and columns for degrees of freedom U1, V1 and U3, V3. Where members share degrees of freedom, the contributions add together. In this way, the global stiffness matrix accumulates the stiffness of all three members, giving us a 6x6 system that represents the whole truss. Now that we understand where to place them, we can now place the actual numbers from each 4x4 element matrix into the 6x6 global matrix in the rows and columns that we discussed. These rows and columns complement the end node degrees of freedom, and we add any overlapping terms. We can pull out a common E times A factor since all members share the same E and the same A, and we'll get the exact fractional matrix. The decimal form is just a convenient check for the code. If members have different axial rigidities, we'll assemble it after replacing their relevant E's and A's into each element. Now that we've seen how the global matrix is assembled, let's look at how we can implement this process in coding. The logic is straightforward. We're going to start with an empty global stiffness matrix filled with zeros. The size will be determined by the total number of degrees of freedom in the structure. We'll loop through each element in the structure, identify the nodes that define the element, and then determine the corresponding global degrees of freedom. We'll then add the element stiffness terms into the global matrix at these positions. If a position already has a value, we'll add the new term on, just as we saw in the example that we just solved. This coding approach replicates the process we just carried out manually. Each element stiffness matrix is mapped into its correct block. Zeros remain in all unused locations, and overlapping contributions at share nodes are summed. In this way, we build up the global stiffness matrix for the full structure automatically. Let's get started. Here we look at the first steps of the code. We always begin by preparing a clean workspace. Clear all removes all variables from memory, close all closes any open figure windows, and CLC clears the command window, so we start with a blank screen. A few important reminders for the coding style. Any line that begins with a % is a comment. Comments are not executed, they're just there to explain the code. Commands that end with a semicolon will run, but they'll suppress the output from being printed in the command window. This keeps the script tidy, especially when dealing with large matrices. These first steps don't yet build the stiffness matrix, but they set out a clear environment so that the code is easier to read and the results are not confused with leftovers from a previous run. We'll use the example that we just solved and begin by defining the node coordinates. Each row represents one node with its ID number and its x and y position in meters. In this example, node 1 is at the origin, 0, 0, at the bottom left of the truss. Node 2 is at 3, 0 on the bottom right, and node 3 is the top node at 3, 4. This set of coordinates automatically defines the geometry of the structure. From it, we can see that member 1, 2 is a 3-meter horizontal bar, member 2, 3 is a 4-meter vertical bar, and member 1, 3 has the diagonal length of 5, forming the well-known 3, 4, 5 triangle. Next, we count how many nodes there are by taking the size of the coordinate matrix. In our case, there'll be 3 nodes. We can also extract the node IDs, which are simply 1, 2, and 3. We then define the element connectivity. Each row here represents one element showing its element number, its start node, and its end node. Element 1 connects nodes 1 and 2, which is the bottom edge of the triangle. Element 2 connects nodes 2 and 3, and element 3 connects nodes 1 and 3. Together, the 3 elements form the triangular truss that we can see in the figure. Again, we can use the code to automatically count the number of elements by checking the number of rows in this connectivity matrix. Here, there are 3 elements. For a 2-dimensional truss, each node can move only in horizontal and vertical directions, so there are 2 degrees of freedom per node in the global system. We store this as num_dofs, the number of degrees of freedom, equals 2. And finally, we need a way to number all the global degrees of freedom consistently. To do this, we create a simple loop. For each node, the loop assigns 2 degrees of freedom. The first is the horizontal displacement u, and the second is the vertical displacement v. For node 1, the degrees of freedom are numbered 1, 2, for node 2 there'll be 3, 4, and for node 3 there'll be 5, 6. In our case, this gives us a mapping from nodes to degrees of freedom that matches exactly what we see in the figure, where each node has its u displacement shown to the right and the v shown upwards. Later, this numbering will be used for when we place each element's stiffness matrix into the correct rows and columns of the global matrix. Now we move on to defining the geometry and material properties. We start with the modulus of elasticity. Here I've set E equals to 1, just to keep the number simple and to check with the results that we got in the exercise that we completed by hand. In practice, we would normally use a realistic value, such as 200 gigapascals for steel. We then create a vector E, which contains the modulus for each element. If all the elements are made out of the same material, this vector will just repeat the same value, as shown here. If different elements have different materials, we could enter them directly. Next, we define the cross-sectional area. Again, I've chosen a value of 1 just so that we can check the results that we get for this coding with the results that we solved by hand. But you should calculate this based on the dimensions of the bar. For example, you can see here hidden as a comment, a 20 by 20 square cross-section bar. As before, we then build vector A, which assigns the area to each element. If each element has the same area, we just repeat the value, as we do in this code. But if we wanted each element to be different, we could enter them individually. And finally, we set up 2 vectors to store the geometry of the members. One is L, which will contain the length of each element, and the other is ang, which will contain the angle of rotation for each element in degrees. At this stage, they're just initialized as zeros. Later on in the code, we'll calculate the actual lengths and angles from the node coordinates and store them here. We now move on to step 3, where we build the element stiffness matrices in global coordinates. First, we set up a 3-dimensional array called KL, or stiffness K for each element. Each slice of this array will store the 4x4 global stiffness matrix for one element. We then begin a loop that runs over all the elements. For each element, the first step is to find the start and end node numbers from the connectivity table. For example, if we're looking at element 1, this tells us that it connects nodes 1 to 2. Next, we pick out the coordinates of these two nodes from the coordinate table. This gives us the x and y positions for the start node and for the end node. With these coordinates, we can calculate the geometry of the element. We can work out the differences in x and y between the two nodes and calculate the length of the element using Pythagoras. From the same differences, we can calculate the cosine and sine of the angle, which we'll then use in the transformation. We can then save the results into two vectors. L stores the length of each element, and ang stores the orientation angle in degrees. With the length known, we can form the local axial stiffness matrix. This is a simple 2x2 matrix multiplied by E times A over L. It represents the stiffness of the element in its own local coordinates, which are aligned with its axis. To relate this to the global x and y directions, we need a transformation matrix. For a truss element, this is a 2x4 matrix made up of the cosine and sine terms, one row for the near end and one for the far end. And finally, we transform the local stiffness into the global coordinate system. This is done with a standard operation T transpose times K times T. The result is a 4x4 global stiffness matrix for the element, which we store in the appropriate slice of KLM. Here, we can see the results for the stiffness matrix for element 1. The loop repeats this process for each element in the structure, so by the end we have the global stiffness matrix for each element in the truss. You can press here to see the matrices for the other elements. Now we calculate the total number of degrees of freedom for the structure. This is simply the number of nodes multiplied by the number of degrees of freedom per node. In our 3-node example, each node has 2 degrees of freedom, so the total is 6. We then create the global stiffness matrix K as a square matrix of this size, initially filled with zeros. Then we begin a loop over each element. For every element, we look up the start and end node numbers from the connectivity table. Using the degree of freedom numbering table we created earlier, we can build a list of the 4 degrees of freedom which are associated with this element. For example, for element 1, which connects nodes 1 and 2, the degrees of freedom are 1, 2, 3, 4, which represent U1, V1, U2, V2. For element 3, which connects nodes 1 and 3, the degrees of freedom would be 1, 2, 5, and 6. With this list of degrees of freedom, we can now place the 4x4 stiffness matrix for the element into its correct location in the global stiffness matrix. The line of code adds KLM for that element into the relevant rows and columns of K that correspond to these degrees of freedom. The loop repeats this for each element in the structure, and in the end, the global stiffness matrix K contains the combined stiffness contributions from all 3 elements correctly positioned according to the degree of freedom numbering. And here you can see the final stiffness matrix. In step 5, we display the results so that we can check the calculations. We first set the display format to engineering notation. This prints numbers in a way that is convenient for structural analysis, using powers of 10 and showing values to a sensible number of significant figures. Next, we print the global stiffness matrix. fprintf displays the title, and the title shows its size, and then the matrix K itself is displayed using the disp or display function. This is the assembled stiffness matrix for the entire truss, containing contributions from all 3 elements. After that, we can print the element lengths. These were calculated earlier from the node coordinates, and we can check the numbers to see that they match what we expect from the geometry, like 3, 4, and 5 meters in our case. And finally, we can display the element angles measured in degrees from the positive x-axis in a counterclockwise direction. These should correspond to the orientation of each element in the figure. For example, the horizontal element along the bottom has an angle of 0, the vertical one has an angle of 90 degrees. This output provides a clear check that the geometry and the stiffness matrices have been set up correctly before moving on to solving displacements and forces. Now that we have the results, it's important to check them against the hand calculations we carried out earlier. On the top, we have the stiffness matrix assembled by hand. We worked through each element, calculated its contribution, and placed the terms into the correct rows and columns for the global stiffness matrix. This gave us numerical values for each entry. On the bottom, we see the stiffness matrix produced automatically. The entries are the same, but MATLAB has carried out the calculations and assembly for us. By comparing the two, we can confirm that the programming output matches the hand calculation. For example, the diagonal terms, which represent the total stiffness at each degree of freedom, are identical in both approaches. The off-diagonal terms, which show the coupling between nodes, also match exactly. This comparison is an essential step in developing confidence with the code. It shows that our implementation of the geometry, the material properties, the local stiffness matrix, and the assembly process is correct. Once we're satisfied that the MATLAB script produces the hand calculations for a simple example, we can then use the same script for larger or more complex structures where hand calculations would be impractical. And finally, it's worth noting that the same script can be run in Octave. Octave is an open source alternative to MATLAB and is completely free to use. When we run this truss example in Octave, we obtain exactly the same results as in MATLAB. The global stiffness matrix, the element lengths, the element angles are all identical. This is helpful if you don't have access to a MATLAB subscription. It means you can still learn, test, and apply the same structural analysis using Octave without any cost. So whether you're working in MATLAB or Octave, the workflow and the results are consistent, and the skills you develop are transferable between the two platforms. So to summarize, in this session, we took the local coordinate systems and transformed each local stiffness matrix into the global stiffness matrix and assembled it together. We also looked at an example of a truss, we solved by hand, and we also coded it. Next time, we'll be looking at how to introduce the load vector, and that way we will have all the components of the stiffness expression F equals K times D, and be able to find the displacements. Join me next time for that.